All right, good afternoon, everybody. We are excited to have you with us for our Forage Forum Friday. This will be our last round of Forage Forums. This is our third round, so we've been incredibly excited to have all the different topics over the last 3 years. And so I know many of you I saw just maybe about 18 hours ago for our annual Indiana Forage Council annual meeting. So I appreciate you guys joining us again today. So we're excited to have Dr. Alan Franzluebbers here with us to talk about kind of soil health and soil ecology. So Dr. Franzluebber is the research ecologist with the USDA ARS in Raleigh, North Carolina, and has really kind of become known as kind of a soil health really expert in this area. He was featured as part of the Missouri hosted Heart of America Grazing Conference just last fall, and we're excited to have him back here in just a couple of weeks for the Heart of America Grazing Conference that the Indiana Forage Council is going to be hosting February 20th and 21st in Ferdinand, Indiana. So if you haven't signed up for that yet, there's still a chance. So thank you, Dr. Franzluebber, for joining us this morning, and we're excited to hear more about soil health today.
Thank you, Alicia. Well, thanks for having me. I appreciate the opportunity to speak to you. I guess I'll get to do that in person too in a couple of weeks, and so I'm somewhat looking forward to it. Although it's in the 60s here today, and I'm not sure it'll be so nice in Indiana in a couple of weeks, but we'll have to wait and see. All right, very good. I'm going to share my screen, get rid of my video, and go from here because I need to keep my bandwidth honest. All right, well, all right, I'll just dig into it then. So soil is important to me, and I hope it's important to y'all too, because anybody that grows plants and has anything to do with agriculture, soil should be something that's very important to them. But we oftentimes take it for granted, and that's kind of why the title soil silently serves. We take it for granted for a lot of times. Soil really fits in nicely with the United Nations ecosystem services paradigm, where they have these 4 categories, and oftentimes we focus on these services in cropping systems, food systems, but grasslands are a food system too, and we should really keep them in mind in that we provide these grasslands provide this ecosystem for food production, for meat production primarily. And that is a primary focus of many of our agricultural operations. So that's nothing new for us. We almost always focus on biomass production or food and fiber production. But there are other ecosystem services too that are probably equally important and sometimes more important in some cases. We should consider the water cycle. The grasslands and the soils under grasslands are very important in cycling water, certainly by holding water, by allowing water to infiltrate, not allowing water to run off and carry nutrients or pesticides with them to our water bodies. So water cycling is extremely important for us. We also want to consider that grasslands and soil under them are important for nutrient cycling. We oftentimes consider grasslands kind of the second class agricultural land use, but that really shouldn't be, because grasslands are providing a lot of benefit to us, and certainly nutrient cycling is one of them. And where there are confined animal feeding operations, grasslands have an enormous benefit because there's land area available for that manure input, and pretty much any time of the year as well. So that's a value because grasslands tend to be more stable. And as far as climate regulation, it's probably not so obvious, but certainly there's a good deal of carbon under grasslands, and so that carbon is being sequestered in the soil as organic matter and taking that CO2 from the atmosphere. But certainly the cycling of carbon dioxide from the atmosphere to the soil, and then of course the soil back to the atmosphere, this is a natural process, and we have to recognize it. But maybe we can modify it a little bit to get more of the carbon residing in soil and providing benefit to us. And then we also have this issue of biodiversity. Grasslands can hold a lot of biodiversity. It's not only the things that we see and that are obvious, such as the livestock or the birds or the small animals that roam around on them, but it's really about the insects and the microorganisms in soil that also are important aspect of biodiversity and something that really contributes to this ecosystem stability within a region. And then there are finally, I think there's an appreciation. Some people maybe don't have it, but I grew up in the Great Plains of the country, and I think open grasslands are something to be appreciated. It gives me a lot of sense of satisfaction to be in open space, to know that nature is all around, that you can see a distance. I appreciate the woodlands too, but there's a different experience that you get from an open grassland. All right, so the ecosystem services from forage and grazing lands, and that's really the focus here is because I'm talking to the Forage Friday series to focus on forage and grazing lands, but the soil services that are provided by these forage and grazing lands. So this really depends on the natural resources that are in a region. So every region has some unique conditions, such as the soil type, the slope, the aspect. The precipitation pattern really dictates, what kind of species can be present, plant species that are present, and certainly seasonal temperature and the surrounding landscape conditions can also affect the resources that are available to any one particular farmer. And that's I think what we should recognize is that there are not prescriptions that we might want to give everybody as like, well, this is the way farming is. No, it's sometimes it's based on the nature of the landscape around the farm and how the resources could be utilized effectively. But there are also these various things that each individual farmer has a little bit of control on, whether there's planting of annual or perennial species, or the functional types of these forages, and certainly the stocking rate and how the animals are stocked over time, as well as fertilization and various harvest techniques. So the land managers do have a lot of control on how grasslands can be managed, but there are also these inherent environmental conditions that kind of dictate some limitations for us. So we really should ask, what do we want soil to do for us? If we just take soils for granted, then of course the soils will give us whatever we allow it to. But we can manipulate it sometimes. And I don't mean manipulate in a bad sense, but manipulate so that we can get better ecosystem services from our soils. So there are some important functions of soil, and that's of course as stated before, the producing plants and food for us, protecting that water quality, cycling of nutrients, supplying water and various plant growth promoting compounds, and enabling this animal habitat within the soil. And storing carbon and nitrogen is a very important function that also then allows for other elements to be stored as well, because that's the carbon and nitrogen are the key elements of organic matter. And then there's a trophic layer where all the other elements are below that. And then buffering against toxic accumulation. We apply a lot of different things to soil, and sometimes we want it to do things for us. And of course, we might want those toxic elements to disappear. And sometimes organic matter processing can do that for us. And serving as a reservoir of biodiversity. So these are all important functions of soil, something that we should recognize. A lot of times we focus only on the production of food and plant material, but there are these other functions that are available for us. But can we manage these functions? This becomes a key issue then too on ecosystem restoration or of just simply sustainable agricultural production. Are we able to fully manage these functions? And if we can, is it going to be very expensive to do? Something that is maybe less expensive might give us a certain level of functionality, but maybe we need to implement some practices that cost a little bit more. And then what rate of change can be expected? If we want to, say, change carbon storage in soil and we want to have 10 tons per acre more, then is that possible within a short period of time, or are we looking at generations of people's time to be able to make that change? So defining these limitations is important, and certainly we need to be aware of that. This tree gives me a sense of function in that productivity is oftentimes our uppermost layer, and we might have nutrient cycling that's also important, water relations, and the branching out into greenhouse gas regulation or even biodiversity enhancement. All of these functions or these ecosystem services that our ecosystems provide for us are really can be defined by some simple metrics. And this metric that I like to focus on is actually soil organic matter. It may not be the total organic matter necessarily. It may be some biologically active fraction, but sometimes it is the total organic matter that's important. And when we talk about soil organic matter, oftentimes we're really measuring carbon because organic matter in soil is 58% carbon. So it's the most dominant element of organic matter. So oftentimes we'll measure organic carbon in soil and express it as soil organic matter for our farming stakeholders. So to define some of these relationships, I want to give you a few examples. And so first of all, the influence of organic matter on productivity. Well, this very elegant study that is conducted at the University of Illinois, the Marrow plots, are very useful for us to understand, well, what is the impact of soil organic carbon on, in this case, corn grain yield or plant production in a more general sense. These data points were taken from this phase 4 of the study. So it started back in the late 1800s. And this phase 4 was from 1968 to 1998. And I'm showing here 3 treatments which were corn, oat, hay rotation, corn, oat rotation, and continuous corn, without amendment on the bottom here and with amendment on the top. So you can see that with amendment, there's an increase in productivity that occurs because nutrient limitations can be substantial. But what you also see in a more general sense is that organic carbon influences the productivity overall the systems. And so there's a positive association between productivity and organic carbon in soil. If we want to have continued sustained production in the long term, then we should strive for higher organic carbon in soil. And that's, of course, organic carbon, but also organic nitrogen that is going to accumulate simultaneously. And if we add in the phase 5 part of this project, where it was 1999 to 2009, a similar relationship occurs, but it's a steeper slope there. And that's probably because of genetic improvement and improvement in the types of management that are deployed in the system. But essentially, the same results are occurring. There's a strong association between corn grain production in this case and soil organic carbon. So there's a real desire for us to increase organic carbon for our own good. And there are literature sources where we can see similar results, where there has been greater cotton lint yield in Georgia, 32% greater in a more diverse rotation that tends to increase organic matter compared to a more continuous grown cotton production systems. Sometimes these studies don't actually make the measurement of organic matter change, but if we had that information, we would probably be able to relate it to why that production occurred. It's likely due to organic matter. And of course, it's only a hypothesis without the actual data, but we do see it in studies where there is a strong association. Another study in Georgia, 11 to 24% greater corn grain yield following perennial sods than when grown continuously. And in this study, they did make some measurements of organic matter, and it was increasing with the perennial sods. In Pennsylvania, 10 to 12% greater corn grain yield following 4 and 8 year sod-based rotations than when grown continuously. So another example. And a final example in Iowa, where there's greater corn and soybean yield in sod-based rotation than when grown continuously. And curiously, in this study, the economics were that there was actually better economic output from this diverse rotation than from a simpler rotation. Of course, the simpler rotations are what's used currently today. But there are some farmers that are exploring more diverse rotations once again, and there can be economic benefit for them. So I also want to explore the relationship between organic matter and nutrient cycling. In particular, I've been recently focused more on pasture-based livestock systems, and I think there's a real need for that because they are present throughout much of the eastern United States, but there hasn't been a whole lot of soil research under pasture-based systems. And in this case, we measured some nitrogen mineralization potential in the top 4 inches compared to pasture age. And this was a kind of a survey. It was a survey of experiments that were conducted on farms, particularly on private farms in most cases, across the whole southeastern region, and mostly in North Carolina and Virginia. But these data were compiled from a tall fescue stockpile trial, but it showed clearly that nitrogen mineralization potential is really a function of pasture age. And the reason why pasture age is the determinant there is because it's the organic matter that accumulates under these pastures. And so with longer pasture time or exposure in the field, there's a buildup of organic matter, and it leads to greater nitrogen mineralization. So oftentimes I get the question, can we predict soil nitrogen availability from soil organic matter? And in general, I think it could be possible. These data would suggest that, yes, in general, there's a relatively good association between soil organic carbon and nitrogen mineralization. You might say, well, is it really relatively good? I question whether it's relatively good. There's a lot of scatter in these data, but there's a good reason why there's so much scatter in these data. And I wanted to give this as an example because the resources that we have in North Carolina, the soil resources, are very diverse. We have soils that are high in organic matter, but not necessarily very biologically active. And this is shown in these data here. So I'm going to express the same net nitrogen mineralization as a function of, well, in this case, I'll explain it here that they came from different regions. And so these different regions are one reason why there's a different association is that there's in the coastal plain, we have this large pool of organic matter that occurs, but it's not very biologically active, leading to greater net nitrogen mineralization. This is partly because many of the soils were submerged. And so there's this organic matter that is highly complex. It's not very biologically active, and it just doesn't lead to a great deal of nitrogen mineralization. Compare that to the Piedmont, where there's more upland soils, it's more oxidized, and that organic carbon does lead to nitrogen mineralization because of the total nitrogen that is accumulated. And the difference between the Blue Ridge and the Piedmont is this would be the mountains versus the foothills of the mountains. And this is partly because the sandy bottomlands are more dominant in the mountains, and that means there's less clay there, and so there's less protection of the organic matter, and it leads to greater nitrogen mineralization. So soil texture can be a determinant of nitrogen mineralization. But if we actually replaced organic carbon on the horizontal axis with a different term, and in this case, replace it with soil test biological activity, these are the same data for net nitrogen mineralization, but they all of a sudden, by expressing it in association with soil test biological activity, we see that there's only one association. It's independent of the region where we took the samples. So texture is still a part of that. Texture is in there, but it's influencing it in a similar manner in that the biological activity is really only looking at the active portion of organic matter, and that's what is needed to actually get nitrogen to be mineralized from soil. So here we would say that well, there's a better way to measure nitrogen availability, and that's with a more active portion of the soil organic carbon, not just the total organic carbon. So I want to move to water relations and the impact of soil organic matter on water relations. Certainly water infiltration is really important, that we get water into the rooting zone so that plants can grow effectively during the drier periods that ensue following rainfall. And these are data from Texas, where the percent ground cover led to greater extent of rate of water infiltration. And so clearly, and these were from Texas in a drier environment, but the ground cover as exposure to the impact of rainfall droplets, this is an important aspect that if we get more of the living and dead material on the surface, rather than a bare ground surface, we're going to lead to greater water infiltration. I think the same kind of things would happen in the eastern part of the country as well. We just don't have a whole lot of those data to share. This is also from Texas, these data here. This is water infiltration. And then at after 6 years or during the 6-year period into 3 different management styles. In the red lines, there's this decline in water infiltration that occurs over the first few years and then seems to plateau a little bit or trough down there. And that's with heavy continuous grazing. So we're removing more of the forage material and keeping it a low condition. And so probably we're getting a little bit less ground cover and probably just a condition that is maybe a little bit more compacted. It's possible. Well, with moderate continuous grazing in the green line up here on top, we see some variations that occur, but it tended to be very stable over time, over the 6-year period. And that's so again, here, this is where the hoof impact might be less dramatic. And so that might be a reason why the water infiltration just simply didn't react negatively to that hoof impact. Whereas compared to this intermediate where we have short duration and high intensity grazing, it's possible that some of this decline that occurred over time may be due to wet periods when the cattle were grazing, and it may have pugged the soil a little bit much. And so one has to be careful with some of these intense management systems that we can not damage the soil. But in general, we as managers, land managers, can control somewhat the water infiltration that occurs on the soil, and that's partly a function of the organic matter at the surface. Okay, taking you to a study that I conducted in North Georgia. We had controlled water runoff conditions. We created berms around 1 hectare plots around pastures, and these data were from these 2.5 acre plots or 1 hectare, and we had 14 of them, and they were monitored with these runoff collectors with the devices that would allow us to be able to collect the or estimate the amount of water as well as the nutrient concentration in that water. So the percentage of rainfall that was lost as runoff was only a relatively small amount of the precipitation, and that was 1.2 to 1.7% across all systems. So really not a whole lot of water runoff that does occur. And that's partly because pastures are very effective in absorbing water. They do dry out, grass roots dry out the soil quite dramatically, but they can absorb that water then very effectively too. So there was no difference in this case when pastures were grazed or hayed. And so that surface condition was maintained in whether there was that grass surface was removed or whether it was grazed and incorporated. So this is another view of the pastures where you see the livestock in the back, and there's a berm around this flume here. So it's controlling how the water flows over the landscape, and it's funneled into this flume here where we can collect the water and then determine the nutrient content. So in this case here, the nutrient loss was enhanced with large precipitation events. And this was over, I believe, if I remember correctly, a 7-year period. And this enhanced nutrient loss really occurred only with large precipitation events, but those were approximately 25% of the events. So a lot of times the small precipitation events do very little for nutrient loss. It seems like nutrients are recycled in the pasture very effectively, but in these cases with large precipitation events, that's where we're getting a lot of our nutrient loss. And in this case, presence of the cattle during these periods caused greater phosphorus loss than without cattle. And that can be important because obviously the defecation by these animals, it's deposited at the surface. And so large precipitation events can lead to some loss of nutrients that occurs. But on average, the phosphorus loss was only 4% of the total from fertilizer and the feces that were accounted for in these systems. And we did apply phosphorus fertilizer on a yearly basis. So there was an application of phosphorus, and of course there was deposition of the feces by the animals. But really only a small amount of phosphorus was being lost. And these are data from across several studies throughout the eastern United States. And there are different numbers of observations that's indicated by the N equals. There were 14 observations for conventional tillage, 14 for no tillage, and only 3 observations in grass systems. And this happened to be in eastern Oklahoma for the grass systems. But these data would suggest that there's a great reduction in soil loss via runoff from no-till crop production, as well as from grass pasture production compared to a conventional till system. So certainly erosion control is really a function of good ground cover, and grasslands provide that good ground cover. If we move to the biodiversity enhancement, there's I don't have a whole lot of data to directly relate with organic matter, but by using pasture-based systems, we can actually change the species composition of these grassland systems. And these are just some images of examples where we can have livestock, we can have poultry, and the diversity of plant species in the pasture. And occasionally we can have larger animals roaming around and smaller animals that are found, such as earthworms, or primarily, of course, the bacteria and the fungi that reside in the soil. And that's really a function of the root material that's exploring the soil, as well as the deposition of above ground plant material for these pasture systems. So the above ground diversity can sometimes influence what's below ground. And in this case here, it's an example that so we can have a strong structural plant diversity. We can have trees in our pastures, and we can have livestock grazing under trees if we have enough light penetration. So silvopasture systems have great potential in the southeastern US and perhaps in other regions. It again depends on the farm landscape. This would not be something that is for every farm, but some farms might have an opportunity naturally to expose animals to greater comfort under these trees. And in this case, this farm, at the time that this photo was taken, this was tall fescue. It was providing great benefit for this tall fescue because this was actually in the flatwoods region of North Carolina, where tall fescue doesn't really do well. But because it was under a little bit of shade and a protection from the extreme heat and the dry conditions, it can do well. But in fact, this pasture was devastated by some of the hurricanes that did come through, and because it was inundated with water for days on end, the tall fescue didn't survive that. So we need to find grass species that are more suitable for that condition. I want to take you through a little bit of an experiment that we conducted in North Georgia of interseeding tall fescue into Bermuda grass sod. We had coastal Bermuda grass planted for 5 years, and then we decided that we want to use the land a little bit more intensely. We knew that we had a good growing season in the fall and the spring, where Bermuda grass just wasn't productive. Bermuda grass is only productive in our region from approximately May to September. And we thought we could get increased productivity with introducing a cool season into a warm season. Now, it might not be for everybody because it takes a little bit more management. And I think the data that I want to share with you suggest that management is very important in how we would actually manipulate these systems. So on the right, I've got 4 scenarios here for you on different forage utilization regimes. And on the x-axis are the years of management. So this is over a 7-year period that we were conducting this. And this is the percent basal area of what we were measuring as tall fescue, which we interseeded into the coastal Bermuda grass, drilled into the winter. And the coastal Bermuda grass was there, planted and exposed there for 5 years already. And then we also measured bare ground and weeds. Now, the bare ground is because we were taking a 1/4 square meter area and expressing how much of the area was in bare ground, coastal Bermuda grass, tall fescue, and weeds. This would not be similar to maybe a point step method, because we would be getting more bare ground area in this kind of estimation. But so the point here is that with when the forage above ground biomass was continuously removed with haying, we were exposing the coastal Bermuda grass to more harsh condition and allowing great exposure of the tall fescue to express itself. This happened to be Georgia 5 endophyte infected tall fescue, which was very aggressive, let's say. And we thought that's what we had to use. Now, granted, I'm not a forage agronomist and I'm not an animal scientist, but I was very curious and interested in this study, and it was an important part of my career. I would say that we could have gotten by with a novel endophyte in this case, and it would have probably been a better situation. Well, we chose the toxic fescue because we thought that the Bermuda grass was going to be so aggressive that we would never get any tall fescue establishment. Well, we were proven wrong, at least under the hay conditions. And so you see that the tall fescue increased in proportion, and the coastal Bermuda grass actually decreased. And the weeds were suppressed as well, and the bare ground tended to just to be stable. Okay, and at the end of the 7 years, the data would suggest that just what I've said there is that the Bermuda grass did decline, the tall fescue predominated, and we were left in this Haid situation with tall fescue that likely would have dominated even further. We would have probably gotten rid of all of our other competition, tall fescue being very aggressive in this case. Now, if we went to the other extreme and had unharvested condition, not too dissimilar of a result occurred. We had this increase in tall fescue, a very rapid increase in tall fescue, and we lost most of our Bermuda grass when it was unharvested because the tall fescue simply shaded out all other species. And we were left with some bare ground that was relatively stable, but the weeds disappeared and the Bermuda grass disappeared. So by leaving the land unharvested and having no cattle impact, we're simply favoring this cool season forage species that had this endophyte in it and was very aggressive. Now, if we add cattle to the system, we can see that, yes, tall fescue also increased in this case where we had low grazing pressure. We were trying to maintain approximately 4,000 pounds of dry matter per acre over the period. And that was our target, but we were ending up being only about 2,000 pounds. But we had this low grazing pressure where we would take animals off when we reached that threshold, and then we would let the pastures rest a little bit and then put animals back on. So it was a modified continuous grazing situation. But what you see is that the Bermuda grass didn't decline very dramatically. The weeds disappeared and the bare ground disappeared. So we had a pretty good exposure where we had a good ground cover, and we had certainly a more dominated tall fescue system than a warm season Bermuda grass. But there may be some advantage to that for some growers, producers. They might want to have more of the tall fescue, and it's really curious because the tall fescue is prevalent in the cool season, and you don't see any Bermuda grass in the cool season. Come summer, when it's hot and dry, you don't see any tall fescue, but you see only Bermuda grass. In the final situation where we had higher grazing pressure, we saw that there was a real balance between the Bermuda grass and the tall fescue. So the point being here across all of these four scenarios is that we as managers can control what the impact of our cool season versus warm season species might be. And we can do that within the same pasture. And this could be an example for using other species, that other warm season and cool season species, where we can manipulate them by how we utilize the animals on the landscape or on the pasture. Okay, finally, I'd just touch on a little bit about greenhouse gas regulation. And of course, in a lot of ways, this is more of my emphasis in my research, is the determining how much carbon actually is stored in soil, and rather than emitted as carbon dioxide or methane or as nitrous oxide. So I'm going to share with you some recent results of this is sampling. We have a very good situation in North Carolina. We have 18 official locations, research station locations, and then there are some subsidiary farms associated with these research stations. So I found 25 research station locations to sample across North Carolina. I did that two winters ago, and the results were really curious to me. So I'm not going to go into the details, but I've recently been calculating root zone enrichment of soil organic carbon. This is a process where a below 12-inch depth of soil, my hypothesis is that, and based on the evidence in the literature, that we're not really changing organic matter below 12 inches. And so we use that as a baseline condition. And in the Piedmont of North Carolina and Georgia in particular, where I developed this idea, it's a real, the data are supportive of this hypothesis, is that we've eroded so much soil away that we're left with subsoil. And so that soil that's below 30 centimeters can be a really good indicator of the actual the baseline condition of any type soil. So this is root zone enrichment, is that carbon that has accumulated in the top 12 inches of soil, minus that of the baseline condition. So it's a little bit of a complicated story, and I'm just going to leave it at that. And we do have some papers, I have some papers recently that explain this. Some are published already, and this one happens to be coming out in the summer in Journal of Soil and Water Conservation. But the point here is that conventional till cropland, we can get an estimate of the amount of root zone enrichment. And then note it's that value is lower than under no-till cropland, significantly lower, but that no-till cropland was not any different than with grassland, and the grassland tended to be lower than under, well, it was lower than under woodland. That was in the flatwoods region. That's along the very coast of Carolina. We also then move inland into the coastal plain where we had more sites that were there. We saw that no-till cropland also was still greater in carbon accumulation in this root zone enrichment than with conventional till cropland. But the grassland now was statistically greater than under no-till cropland. So that's an interesting observation there. And that it was not statistically different than under woodland. Of course, the values are quite a bit different on an absolute condition, but we had a lot of variation among the sites there. And then we move into the Piedmont, we see a similar trend across all of these different regions. Of course, the numbers are a little bit different, but basically no-till cropland greater than conventional till cropland, and grassland tending to mostly greater than under no-till cropland, and woodland having the strongest accumulation of carbon. And then up in the mountains, we have a similar situation. And overall, across all these 25 locations, we could easily say that the no-till cropland is greater in carbon accumulation than conventional till cropland. So many data would support that. Not all studies support that, but a lot of studies do support that we can sequester more carbon with no-till cropland than conventional till cropland. But maybe somewhat surprising, or partly because we just don't have that many data under grasslands, but the grasslands had greater carbon accumulation than under no-till cropland, and the woodlands had greater carbon accumulation than under grassland. So we see this gradient of land use and how it can affect carbon accumulation. Again, this is root zone enrichment of soil organic carbon. Sometimes there's a difference in landscape position, and that's why the root zone enrichment calculation is necessary, because some soils are enriched already in carbon, and it would not be fair to simply use the stock of carbon, the total stock of carbon, because there are differences in carbon accumulation with depth. And that was due to pedogenesis, not necessarily due to management. So I'm going to go through this on total nitrogen. Let's just look at the overall across the 25 sites. This is a curious result because it actually shows very similar in that no-till cropland is greater than a conventional till cropland, and grassland greater than no-till cropland. But what is really curious is that the grassland is now greater than under woodland, whereas under for carbon accumulation, the woodland was the superior land use system. In this case here, certainly grasslands tend to be fertilized with nitrogen. So there's some accumulation of nitrogen that can occur in the organic matter, the total nitrogen that's accumulated under grassland. And also woodlands tend not to be fertilized. And so there's maybe a nitrogen limitation. So there's a difference in the carbon to nitrogen ratio, certainly, but it shows that the fertility, if we look at fertility as a nitrogen source from organic matter, then the fertility of grasslands is much greater than under a woodland even, and certainly under some of the croplands. And that's partly because the cropland situation is either being disturbed and allowing oxidation of organic matter and the loss of total nitrogen, or because it's a simpler cropping system and that we don't have continuous rooting in some of the no-till croplands compared to grassland. So I think we could have more data on this, and I'm trying to collect more data as we speak. And then finally, I wanted to associate this total nitrogen accumulation and looking just at the 25 locations here on the bottom. Very similar results in a trend-wise compared to the total nitrogen. And effectively, soil test biological activity, I would argue, is a very good indicator of nitrogen availability in soil. Not a perfect indicator, but certainly a very good indicator that allows us to express some of these changes in soil from a very relatively simple approach. And taking this further, I just wanted to characterize some of the false stockpile situations where we had, and this was done over a diverse region here in the eastern U.S. states. partly because the only way that you can get diversity in the resource condition is to go to different places. You can't really get that diversity in a single location of a research station. Certainly in North Carolina, we have a diversity of research locations, and this has been done, but we don't have necessarily all of the optimum management conditions. So these were done primarily on private farmers' fields, and total of 92 fields sampled over 3 years. We had a difference between forage utilization of conventional, which I classified these fields into conventional and improved. Conventional tended to be continuous stocking and or haying on the land, and the improved tended to be rotational stocking and with cattle grazing. The pasture age was characterized into 4 components there, as you see, and there were differences, of course, in the coastal plain. We had the most observations in the Piedmont and some in the Appalachian region as well. And then we could also characterize them by coarse, medium, or fine soil texture. Well, the results in the top 4 inches were interesting, and actually in this case, in this study, we only measured the top 4 inches. But this is the effect as affected by forage utilization. And all of these effects were statistically different. We had other effects that were not different, but showed some trend lines. So we have conventional management versus improved management. And of course, the images that are in the background here are my attempt to share with you, well, these were observations that we saw that we had close grazing versus less close grazing. And we can only leave it at that. Maybe we need to characterize that better, but basically we can classify them. And we saw that total organic carbon was increased with improved management compared with conventional management. That particulate organic carbon, this is the visible organic matter that's greater than, well, it's sand-sized material, something that we can actually extract from the soil, the whole soil, and characterize, and that was greater. So there's more either dung material or root material that's actually present in soil that has not fully decomposed. And the cation exchange capacity was greater under improved management than conventional management. And sieve soil density was lower, and that's because there's more organic matter, which reduces the density of the soil. So we can see some effects that are occurring when we characterize these land uses this way. And I would say that in this case, there was no intent behind the study. We just happened to collect. Our intent was to determine nitrogen or the yield response to nitrogen fertilization. And then afterwards, I decided, well, we have all these data. Let's try to characterize them. So I would say that this is truly a survey type approach that really had no bias in it. I can't say that I had any intent in the beginning. So these are observations from, I would say, a relatively unbiased approach, because oftentimes, it's difficult for us to manage in a research station a system that's purely improved versus one that's more typical. We just don't have the ability to manage them so uniquely different. We want to manage them all well. That would be the point. So the organic accumulation in these 92 field sites also was measured. And so we looked at organic carbon with pasture age, and sure, there's a lot of scatter because we had a large diversity of conditions that were out there. We had coastal plain, Piedmont, and mountain regions. We had fine and coarse textured soils. So there is a lot of scatter, but the trend line was suggested that within the first 20 years, we could accumulate organic carbon, and maybe after that, there's not a whole lot of accumulation. And soil test biological activity was very similar to that. But importantly, basically all systems with a more mature pasture, we were able to double the organic carbon and the soil test biological activity in these pastures compared to a relatively new pasture. So there's a reason why we might want to fertilize our new pastures more than an older pasture. An older pasture becomes a more mature ecosystem that then tends to recycle nutrients rather than have a need for improved or inputs of nitrogen. And then finally, just a little bit about soil organic carbon sequestration as by management. We have this 12-year study where we had 5 years of Bermuda grass only, and then the Bermuda grass plus tall fescue, and during the next 7 years. And so during the 12 years, we could clearly see that animal impact was a positive on carbon accumulation compared to an unharvested or on a hayed situation, because the unharvested, basically the land is not disturbed. So obviously, yes, water infiltration was high. It was highest in the unharvested situation because we have no hoof impact, and it was higher than cutting for hay because we have no mechanical impact. But the carbon accumulation, there's a positive benefit by having cattle grazing on these lands. And in another part of the study, we were able to document that the productivity of the grass was better with animal impact compared to unharvested. So there are some positive things that we can get from grasslands, but it's our management that really is important as well. And the final graphic that I'm going to share with you is the cattle stocking rate is an important determinant of the soil organic carbon accumulation. There's an optimization that is out there. If we overgraze, obviously we're going to reduce organic carbon. We don't have as much plant productivity, we don't have the return of the carbon to the soil, and so we're going to start seeing organic carbon decline. On the same, similarly, if we don't utilize our lands effectively, we're essentially allowing the sun to photooxidize a lot of this carbon and not lead to any carbon accumulation. Whereas with grazing, we can get some impact from the hoofs and from the deposition of the material, the utilization of that grass by the livestock, so productivity can increase, and we get a very functional ecosystem that can sustain itself for a long time. Certainly grasslands are part of our landscape, and those places where they have them, it's appreciated by the neighbors that don't have the grasslands. And so our homes are what we make them. We can make them beautiful, or we can allow them to bother our eyes. And certainly, I just think that we do need to reflect. We need to consider what's important for us. We all have maybe some different values, but we also have shared values. And those values can be that we build each other up, and perhaps we can find ways that we can utilize our landscapes more effectively, so that we're able to sustain our livelihoods and not necessarily pollute the environment or cause others harm through our activities. So in summary, I wanted to just make a few statements that could maybe wrap this up. That foraging and grazing lands can be highly productive to provide feed, food, and fiber from the livestock that thrive on these ecologically stable lands. And certainly having more diversity of the plant species can be a very good thing, but maybe too many species is not so good. It depends on what the goals are. If it's only based for wildlife, then maybe a lot of species are important. If it's based on the livelihood is based on livestock production in a pasture system, maybe not so many are also good. Maybe there's an optimum level that we have to make sure that there are productive forages out there that are leading to good gain from the intake. And forage production can be managed to enhance ecological and environmental services like soil carbon sequestration and biodiversity, but they can also be managed poorly to create environmental problems with water quality and climate change. And we have these examples in our landscape and in our country today. And we can decide which ones we want to have. So it's our choices to make, and certainly staying informed is a good thing. And hopefully we'll have good research and good outreach and collaboration with stakeholders in the future. So thanks for the opportunity to share this with you. I will try to take any questions that you might have.
All right, thank you, Dr. Franzluebbers. So we do have a couple of questions that have come in the chat box, and pull those up real quick. And so while we're asking those, I do have a very short poll, if you wouldn't mind answering those questions for me. So we'll start asking questions. First is, can you kind of explain what cation exchange means in maybe a little more simpler terms? So what is the MEQ over 100-G? So kind of just a little more simplified.
Sure. Okay. Well, the cation exchange capacity is really about the cations like calcium, magnesium, potassium. Those are elements that have a positive charge, and they're attracted by negative charges, either from soil colloids or from minerals or organic matter. And it's an attraction that occurs that allows those nutrients then to be present in the soil surface, so that plants can then utilize it. They're exchangeable. It's essentially a way of telling us how attractive is the soil for these nutrients that are needed by plants.
All right, thank you. Second question is Alan Savory right about grazing animals being properly managed through a series of paddocks? Does this restore grasslands? That makes sense.
I think I understand the question, and certainly there are opinions about this. I think, you know, it's he's shown very clearly that some lands that are highly degraded can be restored. You know, I'm out in the field right now. We're implementing a bale grazing study. It's not common in the eastern United States. It's common in the western part and in the colder northern place where it's frozen over winter. But animal impact can have a negative or a positive impact. And we're trying to get the positive impact at an optimal level and avoid the negative impact at too high a density. And so Alan Savory, I think, I don't want to put words into his mouth, but I believe that he probably thinks that we've overutilized some of our grasslands, where we basically are continuously stocking and essentially creating landscapes that are now unfavorable for livestock production because the plant species that we desire are no longer there. And so certainly moving animals and having rest of the grassland is probably the most important aspect of that rotational stocking. But it allows then the roots and the beneficial plants, the ones that we want, the desirable plants that we want, to proliferate and to allow animals then to have forage that they can digest, that they can gain on. And that so controlling animals is important. We do that as land managers, but when we don't control them, then we let the animals decide for themselves, and they know what to do. Consume all that they can in the shortest period of time that they can. So I don't know if I really answered the question, but yes, I think there are opportunities to restore the grasslands with managed grazing. Absolutely.
All right, thank you. So our next question, how would you adapt a tall fescue Bermuda grass stand system for kind of more temperate Indiana? So obviously we have a little more cool season is preferred here.
Sure.
Would it maybe be more of like a tall fescue crabgrass mix, or what would you recommend?
That could be very possible, right? Bermuda grass is probably not going to proliferate in your region. Yeah. I don't know. I you know, tell you the truth, I haven't been in Indiana much, so I'm looking forward to in a couple of weeks. I suspect, though, that Bermuda grass doesn't do well. But there are probably other species, and crabgrass, being an annual species, certainly has value. We know that it has value here in the South too. We have tall fescue fields, and annual crabgrass invading them in the summer can be very good. It provides digestible forage, and tall fescue tends to dry down in the summer. So the infrequent rains that we get, crabgrass can be very good. It just basically covers up the tall fescue, but come fall, when it cools down and we get more consistent rains, the pastures are fescue again. It's a great system. So I think that could be also, you know, one could use, certainly in Indiana, one can consider maybe not in the same pasture, but having a diversity of pastures where you focus on, say, native warm season grasses or other perennial warm season grasses. And it could be annuals too. It doesn't always have to be in the same pasture. One can have, you know, dividing in space as well.
Thank you. And then what do you recommend is kind of an optimal stocking rate? 2.5 acres per animal units, or just depends on the diversity and kind of what you have available?
It's a really good question. That isn't really my expertise, but I'll just take a stab at it. I think the environment really dictates that. So even say the environment in Indiana could be very different, because it's the soil resources, your accessibility with water, with elevation on the farm. Those things should matter. But in general, you should be able to say, well, is it 3 acres per animal, or is it 2 acres per animal? Those yes. Perhaps 2.5 acres per animal is a good stocking rate in the end. I really don't know.
Yep, that seems to be kind of that we don't know question. It's definitely greatly different, varying state by state, region by region. So, yep. Okay, so why didn't the Great Plains grow trees? Why did they remain grasslands?
Well, I did grow up in the Great Plains, but my grandfather had already plowed the sod before I was exposed to it. So I don't really know. But from what I've read, certainly fire was a part of it. Fire controlling the tree growth, and it's used as a management tool these days of burning native worm seeds and grasses so that the brush can be controlled, the trees can be controlled. Certainly, but also the environment in the Great Plains was not very conducive for tree growth. It was windy, it was hot, and it was relatively dry. So these things, and of course there were some wet years in there too. Perhaps, trees could grow. But the farther east one goes, then of course there are more trees. And, even in Nebraska, where I grew up, there are trees in the bottomlands. They do occur. And it seems to be, it's a matter of water. You got to have water for trees. And so that would be the simple answer.
All right, thank you. And then this comment was, I have read that grasslands have increased 15% on the planet. Do you find that might be true? Are we making progress on sequestering carbon in cooperation with nature?
I don't know if the grasslands have increased 15% on the planet, but it's very possible because we do have land abandonment, because grasses tend to invade lands that were previously cultivated. So that can occur. I just really wonder if on average or on the bulk, we've done a good enough job with management. I think we still tend to overgraze. And I'm thinking more maybe outside of our country, that people are stressed. They're trying to make a living, and animals roaming freely on the landscape do occur. There are different social constraints in other countries, and so I think we have still a ways to go on actually controlling better grassland management.
All right, thank you. We have a comment from Mr. Loudon that said, in southern Indiana, karst grassland, which is about 150 acres of grassland, they found that more paddocks with shorter rotations actually helped them improve their soil tests over the course of 8 years. So that was just some information that he had. So beyond that, do we have any other questions today? All right, seeing none. Again, thank you so much for being with us today, Dr. Franzluebbers. We greatly appreciate it. And we look forward to hearing you in person in a couple of weeks at the Heart of America Grazing Conference. So,
very good. Thank you so much. Appreciate being with you.
Thank you. All right, so thank you all for being with us today. And we look forward to seeing you again next week on February 17th, again here at noon. So thank you all and have a great weekend.
Bye.
All right. Thank you.